So, hi everyone, welcome to the first binary exploitation talk. Unlike most of the other talks at CyberSoc, this is going to be rather theoretical, with the actual hacks appearing after a lot of talking. I could just get you to memorize a couple of steps to solve some CTF challenges, but that would be completely useless in the real world, and the challenges that can actually be solved in this way are worth very few points. This theory is going to be quite hard. Most students aren't taught this stuff, not because it won't help them, but the universities believe that the results you do get are not worth the effort of teaching them. I disagree with that, and so I made this talk. And bear in mind, unlike most exploit vectors, in which a large amount of can be achieved by running some tool or copying something from Google, pretty much all of the exploit discovery of this class requires both a degree of manual exploitation and creativity. As a result, the hacks you do get look really, really cool and often get you an unfairly large number of points when compared with the time you put in, but you have to sort of sit down and understand it first. But I still want this to be grounded in the so-called real world, so I'll be demonstrating a simple exploit of this class. Yes, the next slides will be available afterwards, do not worry. Right, let me bring up the terminal. Cool. Let me just check it's possible to see it. Cool, so in this folder, I've written a simple program that repeats everything you type. There. It's written in C. I've got the source code here. Let me walk you through it quickly. So, in case you haven't seen C before, I'll just quickly explain. These things here just import some standard functions, a bit like import in Python. This is our main function. Here we allocate 32 characters worth of space. We read a line into this space and check if it's bigger than 0. And if we succeed in reading the line and it's bigger than 0, we print it out and then loop again. So once we receive a line that is 0 long, or for some reason it can't read another line, it stops looping, and we go down to here, where it returns 0. So, a very standard C program, nothing particularly interesting happening here. And actually you can see the empty line thing here. If I do that, it just exits back to the terminal. Now, there's one final file I'd like to show you in this directory. It's called exploit. From the name, you can probably guess where this is going. It's not really a text file. It's got many bytes in it that don't translate to valid characters. You can see all these question marks and weird spacing here. So it's probably best to give you a hex dump of the file. Now, at this point... Oh, it's too small. Ah, sorry. I can make it bigger. Is that readable for people? I'll just wait for the stream to go through. Is that good for people? Can people read that? Good, thanks. Okay. Let me just bring back the source code then, because that's kind of important. The include statement, main, and it's messed with my colours, so give me a second. I have not prepped my terminal for this. Normal copy. Text, custom font. There we go. So, anyway, so you might be asking at this point, Harlan, why are you showing me this? It's really boring. These are just like some basic files, and you're pretty much right. All of these files by themselves are completely uninteresting. They don't do anything, they just repeat stuff. It's rubbish. But I'm going to show you something interesting. If I type out the contents of the exploit function and then type in whatever input I give it, so that's basically send the first line as exploit and then just use the program as normal, and pipe that into repeat, you'll notice that it doesn't actually print all of the characters. What's even more interesting is what happens if I try and get it to do something. So I'll try just, the string echo, and it doesn't even repeat it back to me. Well, let me try something else here. Now that's definitely not what I typed in. In fact, what we have here is a shell. if you don't believe me, you can see the output of strace, which is a program that gives you an overview of what another program does. I'll just quickly abridge this output. Here you can see that execve replaces the current program with the named program here, these arguments, and these environment variables. So this basically just sets up the program. Then various stuff happens we don't care about. And then here, it runs execve again. Except it replaces the current program with /bin/sh, the shell, the program that we can use which we saw at the end, where it was, listening to the input I was giving it. So why has it decided to do this? If we go back to the source code, nowhere in this source code does it tell it to repeat it. All it says is does it tell it to open a shell? All it says here is to read a line and print it again. It doesn't. Where is the shell in this code? All that happened is I said some magic words at the beginning and it suddenly turned itself into a shell. So where did it come from? To understand that, we're going to have to brush away some of the abstraction we use to write a computer program. You can't possibly write a deep learning Bitcoin miner, or whatever else you people write these days, by keeping track of every electron moving through your CPU. Instead, we like to think about programs at a range of different levels, all building on top of each other. At the very top, we have the behaviour of the program, what we told it to do. This is expressed in the source code of the software, the repeat.c file we saw earlier. However, as we saw, the shell does not even exist here. We only told the program to repeat the lines back at us. Lower down, we have the instructions. These are what all programs ultimately end up as, a sequence of instructions that are sent to a processor in order to achieve what we ask for in our code. As this is what the CPU is executing, our shell must exist here in some form, but the actual idea of a shell, or any real structure at all, is very fuzzy at this level, and it's very difficult to think about a computer at this level. And of course at the bottom we have the physical hardware and the quantum mechanical processes that it relies upon. As programmers, we do our best to ignore this level entirely, and I don't even understand it, so I'm going to ignore it too. However, pretty much everyone is taught exclusively at the first level, and occasionally being taught some odd, interesting facts about the second. Pretty much nothing is taught on the level between, where the instructions connect up to the program. I mentioned some of this in my reverse engineering talk, but even in that I still distance myself away from it as possible. So I will share this forbidden knowledge, and with it you can use it to hack many computers. Where does the computer decide to write data? Where does the computer decide? How does the computer decide what code to run next? Knowing the answer to these questions can be used to fix a large number of bugs in software, but actually understanding this answer allows us to take advantage of it. So, here we go. I will launch this. Here we go. I'm going to be talking about the x64 architecture on a Linux system here, as this is where I feel the most comfortable, and this is probably what you'll come across most in CTFs. However, most of the ideas I talk about here are pretty much universal between machines, with only slight differences in data size, naming of things, and algorithm order between systems. Sec. So the processor presents something that's called a virtual address space to each program, which is controlled by the operating system. This allows the CPU instruction to reference a position in memory by a number from 0 to 2 to the 47 minus 1, a number that's known as a virtual address. Often we just drop the word virtual, calling it just an address, because we don't really care about how it's implemented. This virtual address space is split into chunks called pages, which have 3 important flags. These flags tell the CPU whether it can read data, write data, or execute data in this area. Remember, the CPU only sees numbers, so it can't tell the difference between instructions you give it and data you put into it. So it needs this to sort of separate those out. There are, of course, many other flags associated with pages, but again, I'll skip these as they aren't too relevant to what we're doing. So just quickly as a recap, it's important to notice the virtual address space is built out of many, many small blocks of memory called pages, which we can set these control bits on. So let me open our repeat program in a debugger. I have a extension to the standard debugger called Jeff. You don't need to worry about it. The commands will be pretty much the same for you. So I'll run it. The program runs as normal. I'll interrupt it here, and I'll just type in vmmap. So this will show you the memory areas and what they're marked as. So we generally bunch together the pages that are of similar stuff. So we put all the executable pages next to each other because it makes things easier rather than having to guess which bits of memory do what. We just mark an entire area with these flags. So here is where each area starts, each section as it's generally known. Here's where they end. Here's the offset, which relates to the representation of the program in the binary file, which we can skip for the moment. Here are the permission bits I was talking about, and here is where the actual section is loaded from. So here we can see it's loaded from the program repeat. So this is a read-only page, so are this and this, and so that probably holds things like static variables that don't change, like strings, for instance. Here is a readable and executable section, and this actually contains the instructions that get run for our program. In fact, if you look at the instructions here, you'll notice that all of the addresses to code are within this range. And so that's how you can be confident that this is what this is. But you can take my word for it. This is where the code ends up in this section. Later on, we have a readable and writable section. So this is probably where non-constant, mutable static variables are stored. Those things you're told not to use. But we still have a section for them anyway, because occasionally you need them. Here we have the heap and the stack, which I'll go into in just a moment. And here you have VVAR and VDSO, which are special areas that are used by the kernel. Uses those flags I chose not to talk about. You can pretty much go your entire life without caring what these things are. I certainly do. It's just used to make system calls slightly faster. But notice something about the stack. In fact, it's actually underlined it because it's a very rare thing to happen. This stack is readable and executable, which is odd because it also is writable. You can modify the data here and then execute it. So if we could find some way of, during the program's lifetime, writing data here and then getting the program to jump to it, we would have complete control over the execution of the program. So that's really important. I'm going to say it again because this is like the central idea of everything we do here. If we can get the program to execute instructions of our choice, then it's our program. We can get it to do whatever we want. So let me bring up the source code for the exploit file, because it isn't just some random bytes. I actually did construct it. Exploit.s. I've written it in assembler. As you'll see here, this is the padding and an address. We can skip over this bit for a moment. I'll explain this later. But here is the actually important bit. This sets the RAX register to 59, which if you look this up, is the ID of the execve function we saw earlier. Then we can see that we've got load the address of str into RDI, str being /bin/sh, the path to the shell. This rel thing here means that instead of trying to use the absolute address of str, we use the address of str relative to the current instruction, which is useful because we don't know exactly where in memory this is going to be launched. This could be written, this could be written at the beginning of the stack. It could be written somewhere completely different. But we all know that this code and this code will be right next to each other, so this value will stay the same. these are the arguments and the environment variables. We don't care about these, so we can set these to 0. And this finally tells the kernel to execute the command we've written here, run the execve function. So because of the way I've structured this assembler file, we can actually just assemble the source, the code from the file exploit.s, so nasm felf 64 exploit.s, which will turn the assembler code into machine code, and then we can link it, so that means basically turn this machine code into something that can actually run. And then finally, if I run it, notice how we have a shell. And if we actually look at the strace of this, we can see that right at the beginning we have the execve exploit.bin, all this stuff. We run it as normal. Then later on, where's it gone? There we go. Later on, we replace the current thing with the shell, with null arguments and null environment variables. And this is exactly what happened in our repeat code. We repeated this actual code is what got executed somehow from our input. So that tells you what code we can write there. And you can find copies of this code pretty much anywhere on the internet. The term is shell code, because it's code that makes a shell. It's very inventive, I know. But I just wrote my own one here because I'm in a rush. But of course, just because we have some code we can execute doesn't mean that we can convince the program to execute it. So how did I convince repeat to execute that data? And where was that data stored anyway? To explain the answer to that, I need to explain what the stack and the heap are. So, let me go back to the presentation. So, the heap is one of the places that dynamically allocates memory. There are 2 operations associated with it, malloc and free. Malloc is a function that requests a certain size of memory. If there's some lying around in the program, it will be marked as used, and a pointer to this memory will be returned to the person who called the function. If there isn't any memory just lying around, the request is forwarded to the operating system, which will try and find some more space to give it. If there isn't any space left to give it, the program is told it can't have any more, which is known as an out-of-memory condition, and generally results in the program crashing. Free does the opposite. It marks the given memory you pass it as unused, and if there's enough memory next to each other, known as contiguous memory, the operating system is told it can have it back. And this allows it to repurpose it for other processes. Of course, if a program forgets to free memory, then the operating system can't take it back to give to other processes, or even the same process. And eventually, the program and the entire operating system will run out of space. In this situation, the operating system may choose to forcefully kill a process in order to reclaim its resources so that the entire system doesn't just grind to a halt and stop. Once again, there is a vast deal of complexity in the actual implementation of this, such as how the program tracks its own memory, how the kernel stores rarely used parts of the memory on the disk, and how the program optimizes for contiguous memory. This is probably one of the oldest computer science problems, and of course I will stay well away from the actual details of this, as it could easily have, and probably does have, its own uni module. Actual exploitation of the heap is something we can look at in a future talk, but this sort of background should be enough to get you started on that journey, and frankly is more than enough to understand the rest of this talk. So, the stack. The stack is rather similar to the heap. It's got, again, has 2 operations, one for allocating memory and the other for releasing it. However, the allocation function push is of fixed size. You can't say how much you want. You get a specific predefined chunk of memory. And the release function pop always releases the most recently pushed area, which means that you can't release some memory you've acquired unless you release everything before it, everything you acquired after acquiring that first bit of memory. Due to this sort of much more rigid structure, it's a lot faster to allocate on the stack than the heap. And since the structure is actually rather simple, you also can get performance benefits that way. But of course, because you can't free things out of order, it can't be used to allocate large amounts of space. In fact, on most operating systems, it's limited to about 64 kilobytes. That varies between OSs and you can change flags. But generally, if you want to allocate something that is of, multiple kilobyte size or above, don't put it on the stack. Because if you have too much on the stack, the program will just crash because there's nothing it can do at that point. So I'll be talking about the implementation of the stack in this talk, as it's rather simple. So, we have, in the stack, we have 2 pointers. We have a base pointer, RBP, and a stack pointer, RSP. RSP tracks the top of the stack, and RBP tracks the bottom of it. When we push a value, so let's say we go over here, it says push 5. When we push a value to the stack, oh yes, actually that's one thing I didn't mention. The heap when the argument is how much memory you want, the stack is the value you want to store. Because it's a fixed size, and the size is usually quite small, there's no point in an argument of the size. It is quite easy to have it be the argument of the value you want to put into it. So if we push 5, let's first of all set up the base pointer and the stack pointer, pointing at the top. So if we push the value 5 into the stack, first of all we write the value 5 here, and then we move the stack pointer along for that space. So if we want to push another value, we put 5 in there, and the stack pointer would go up. The opposite function, pop, will take the value in the previous bit of the stack and store it in the argument. So here, it will take the register RAX and store the value 5 in it. So if we do that again, so pop RAX, pop that, it would take that and store it in RAX. So this stack pointer always points at the sort of the next available slot of memory, which is, quite a useful way of thinking about it. But bear in mind that when you pop, you're taking the value just, before that, as it were. So if we push the value 6, this gets overwritten with 6, and we move the stack pointer along. Notice how we didn't delete the value 5 when we popped the thing, because there's no point, right? It's going to be overwritten at the next push. Nothing else can see that value. And overwriting it would cost valuable time that could be used to do something else with the computer. But, of course, sometimes people continue to reference an area of the stack even after it's been popped off. And at that point, if people continue to reference it, if it's overwritten by something else, all of the things that expect it to be some other value will suddenly have the value changed underneath them without expecting it. And this is a class of really nasty bug called use after free, because it's been freed, but you're still using it. This can also be used in a security context, which I'll go into in a future talk. But for now, we can forget about that exact thing. It's just important to have at the back of your head. So, one last thing. Notice how the addresses here are going down. That's because, for various very confusing reasons, the stack grows down. When I push a value onto it, I actually decrease the value of the stack pointer. There's a whole history. I don't fully understand exactly why, but it's just important to keep that in your mind. When you see someone subtracting from the stack pointer, that's actually making the stack bigger. And when someone adds to the stack pointer, that's making the stack smaller. But yeah, I think that's probably enough basic background. I'll get into the actual meat of the talk. So, we've got this state. So our next instruction here, is call main. Now, call, I went into a bit in the previous talk, but it's basically like jump, except jump just goes to a place, so there's no way of knowing where you came from. Call pushes the address of the next instruction to the stack. So the next instruction here, let's say, is at address 100. It would push that to the stack and then jump to it. This means at some later point, the code can read that value and work out where it came from, which is very useful, for instance, with functions. Hence, call. When you call a function and then return from it, you want to end up at the bit just after where you called the function. Otherwise, there's basically no point. So I'm going to just quickly walk through how a program a function sets itself up, and then explain why. Push RBP. So that pushes the current value of the base pointer to the stack. That's 30. So we write 30 to the stack, increment the stack pointer. Next, we move the base pointer to the stack pointer. So we set them equal to each other. So this effectively has created us a new stack. The bottom of the stack is now here. All of the previous stuff is outside the stack. It's basically safe from anything you could do within the stack. So then we'll allocate ourselves 10, that's hex 10, so 16 bytes worth of space. So we're pointing here, so that would be 1, 2. And then we can talk about these areas here. So let me explain why I went through all that. As well as storing return pointers, the stack has one other really, really useful job. We store local variables for a function inside the stack. Now, you might be asking, why? Why do we store variables right next to random other pointers to code? It doesn't make sense. Well, if we look at what happens here, after we do this, we can follow this very simple procedure. Move RSP RBP, pop RBP, well, move that down, that's 30, so that goes to 30. Ret, so that returns. And so that returns to address 100, which is here, and the program holds. If you notice, the way of what we've managed to do here is have an area, if I can go back here, we had an area over here which would exist for the whole lifetime of the function and then automatically delete itself, free itself up after the function returned. And this can be done with any size of variable, as long as, of course, you don't go over the end of the stack. This can be done with any amount of variables, which means that, and not only does this work does this empty itself when the program returns, but it creates a new one each time you call a function. This means that the memory can be trusted. This memory can be trusted not to be messed with for the entire lifetime of the function, even if we call a different function, or even the same function itself, because calling the same function itself will create a new area here. This sort of area, the return pointer up to the end of the variables, is known as a stack frame, because it's its own mini stack. So this is if you think about it, the best way of storing variables. It automatically cleans itself up really, really quickly in a way that doesn't collide with anything else and can be relied upon completely. Of course, if you continue to reference those values after the function returns, you'll have use after free bugs with your program, but we'll assume here that everyone's behaving nicely. Now, notice how I reference it relative to the base pointer rather than the stack pointer over here. That's because for the entire lifetime of this function, it only sees the base pointer as saying the same. When we call another function, it will change the base pointer, but when it returns back to our code, the base pointer will be returned to its original value. So all the code within the function sees the base pointer as the same thing, so we can just reference it relative to this. And of course, that instead of using an absolute value, where we wouldn't necessarily know where we were inside the stack, this is the same value for each. This is a different value for each function in a chain of function calls. So, here's the interesting thing though. We wrote the value 5 to this bit of memory here, this variable at RBP minus 10. What would happen if we wrote beyond that. So we had a program that would copy data to this variable, but didn't check where it ended. Well, let's say it just kept copying 5s. The first value would be 5 here, then it would write 5 here, then it would write 5 here, then it would write 5 here, and write 5 here. And let's say it stops here. I mean, it doesn't really matter, it could keep going, whatever, but it stops at some point. Now let's see what happens when we try to return from the function with this sort of corrupted stack frame. First of all, we move the stack pointer to point at the base pointer, just as before. Then we pop the base pointer, and that ends up pointing over some random variable over here, like beyond the end of the stack. It's not the nice 30 it was at before. And then we popped it, so we go here, and then we hit this instruction. This instruction is really interesting, because at this point, we pop the value from the stack and jump to it. This value here is where we go to. So instead of returning to 100 over here, that doesn't happen. We end up jumping back over here. We've redirected code execution from the main code of the program to the stack. Now, obviously, we haven't written anything here, and this will probably contain either zeros or some random other values from a separate function call, and so the program will crash. But we've changed where the code is going. And, you know, instead of getting it to jump to 5, we could write a different value here. We could get it to jump to, let's say, I don't know, 200. And if I can scroll down a bit, there we go, a bit more. You can see that we have a bit of code here that doesn't get called, because once this thing returns, it halts, which prints the flag. And you'll see this in quite a lot of CTF challenges. You can just overwrite the return pointer. Instead of jumping to 5 or to 100, it pops this value, 200, and jumps to it. And you can do a lot of CTF challenges. You can actually do a lot of real-world exploitation in this way. There could exist a function somewhere in the code that actually does some useful thing, like open a shell or install something. It's quite common that they'll have a function for that. And you can just, by writing past the end of a variable, you can end up overwriting that return pointer with a normal flow of code to something, get it to jump to a place of code that you actually want to run. Of course, we saw that we could also jump to the stack. Since we control this area 10, if we wrote the value 10 here, look what happens. We're now executing at code we set. Instead of overwriting the value 5 here, what if we, for instance, wrote execve, sorry for my awful handwriting, /bin /sh. Obviously, the instructions do not look like this, but imagine, for the sake of argument, that it did, right? If I jumped to the value 10, the code would start executing here. This would basically allow us to execute any instructions we fed in. And this is what we saw earlier. We saw that somehow I was getting the program to jump to some code I'd written, which was in a local variable in the stack. Remember, it was a local function variable. And it was jumping to that code and executing it. So if I go back to our code here, I'll explain what the padding and the random number here is. So this data here is 40 bytes long. If I bring up, actually, I can open 2 terminals at the same time. Nano repeat.c. This is 40 bytes long. This buffer is 32 bytes long, and then we've got an extra 8 bytes for the base pointer of the stack, if I bring that up. Remember, we had the base pointer, then the return pointer. So we have to overwrite the local variable, and then the base pointer, and then we get to our data. So that's 32 plus 8, which is 40. So this gets us up until the end of the base pointer. Gets, of course, reads a line from the input and puts it here. Then I have this number here. This is the address I returned to. And if I open it up in GDB, so I'll run the program again, and then have a look at the instruction at this address, you can see that it says push RSP. It's push RSP and then ret. So why have I told it to return to this bit of code? What's special about pushing a register and then returning? Well, push puts it at the top of the stack. Ret takes the thing at the top of the stack and jumps to it. So this bit of code here is equivalent to jump RSP, the stack pointer, the thing we control, right? Because at this point, because it's been popped from the top, the next thing at the stack, because we've just taken this off, is our code here. What we've just done here is jump to the beginning of our code. Now, you might ask why I didn't jump to the stack directly, and the answer to that I'll get on to in a minute is because the stack isn't necessarily always in the same place, and it's easier to jump to a piece of code that will work out where the stack is for you, and then go to it. So if I, sorry, give me a sec. So let me just, oh yeah, that's it. I need to bring up the slides. So what did I do here? I padded the exploit out. I replaced a return pointer with a useful gadget of which jumps to the stack pointer, and then I just ran some shellcode. Cool. So, of course, you don't always have access to the source code of the program, so you can actually do this from scratch, and I'll quickly demonstrate how you do that now, because that's the actually useful bit. So, first of all, you need to actually find out if this vulnerability exists. And since this vulnerability is caused by writing past the end of something, the best way of checking is to spam loads and loads of letters over and over and over again with the aim of overwriting something important. Now, it didn't crash there, but that's because the program's still looping. It hasn't returned. If I get it to return by sending an empty line, I get a segmentation fault. Now, a segmentation fault, a seg fault as it's usually known as, means the CPU tried to access memory in a way that it shouldn't have. That memory might not exist, known as unmapped memory. It might have tried to execute an area that isn't marked as executable, or write something into an area that isn't marked as writable. If I open it up in GDB, we can see exactly why it crashed. I'd like to point out, of course, that just because your program segfaulted doesn't necessarily mean that it's vulnerable to this exploit. It just means there's something wrong with it. So I'll go and copy our lot of A's, trigger the bug again, and boom, we'll get a bunch of useful stuff. This is from the plugin I have. Generally, it won't give you this useful stuff, but whatever. If I have a look at the stack frame, so I can write info frame, or just if, one of the two is fine. Info frame and if are the same thing. You'll notice here that the number 41 appears a lot. 41 is actually ASCII for the letter capital A, the letter I spammed. And you'll notice here, arglist at 0x41, 41, 41, so A, locals at A, blah, blah, blah. But you'll notice here, saved RIP, the saved instruction pointer, the return pointer, is set to A. This means that our input has overwritten the return pointer, and this confirms that the vulnerability can be exploited. This shows us that you could write an arbitrary value here into the safe return pointer, wherever it is, and you would have access to the system. You'd be able to redirect code execution wherever you want it. So, we need to find out how many bytes we need to write before we go to the return pointer. Because if we write too many bytes, we'll just end up with this saved instruction pointer being A, which isn't valid memory, and will cause a seg fault that actually triggered our knowledge of this bug, right? We want to make sure that we don't jump to invalid memory. We want to jump to something we want. So we could brute force this by just decreasing the number of A's I typed in until it stops overwriting the return pointer. Or you could use what's known as a De Bruijn sequence for the input, which I wrote a nice program for. You can find some various things online to do it, or you can just git clone it off me. I don't really care. The De Bruijn sequence is a special sequence. I'm going to generate one of order 2 here. Oh, whoops. There you go. And the De Bruijn sequence is special in that it has every single, or at least of order 2, it's every single pair of letter appears exactly once. So AA will appear exactly once here. AB appears exactly once here. ZZ will not be found anywhere else but here. This means if I get a small substring of some output, I will know exactly where this thing starts, which is very useful. If we can find out where the return pointer starts getting set from, we can work out where in the sequence that is, and it makes things a lot easier. So let me do that quickly. So I will run our program again with this input, and you'll notice that it crashes again. But if we look at the frame, we get this. It's not AAAA, instead it's UA. So if I can bring this up, yeah. Now, because it's little endian integers, it's actually read back to front, so that's why I said UA, not AU. It's a bit confusing, but my program has a simple lookup function, and that gives me the offset 40, which is the value we had before. Of course, if you don't want to read hex values, I had to look them up, I did cheat. You can instead, since we know that the return instruction failed, that means the stack pointer is still where it was before, which means that the stack pointer is currently pointing to the return pointer. So, if we just get it to dump a string starting from the stack pointer, we'll get this lovely stuff, which is the rest of everything from the stack pointer onwards. And we can see it begins with UA, which gives us our offset. Of course, if you use the Chef plugin, it actually just gives you the stack straight out without you having to do this stuff. And you can just see the first two letters here are UA, which is much easier than having to type in all these bloody commands. So we've got the offset 40. That's all very well and good. So let me just copy and paste the string up to that UA. So if I run this, the program will crash in a very interesting way, which you'll notice is not actually, this is it trying to set a value. This isn't actually it jumping something. If I look at the frame, the instruction pointer isn't at all weird or wacky. But if I start putting A's here, so let's put 4 A's, it will crash. Oh, wait, no, it doesn't. Okay, cool. You'll notice that it crashes at the address 4141. Oh, yeah, it crashes here at the address 41414141, you know, the AAAAA bit. So, I can now pass in a pointer. So if I press Control C, I could get it to reload main. So if I get the ASCII value, so printf this, and then I'll write in the hex values of that manually, AE, DF, 43. Again, it's little endian, so I have to write it back to front. And then I'll write some nulls, so back to 0, back to 0, back to 0, back to 0, back to 0. Cool. Into /temp /me. If I run the program again with that input, yeah, there you go. So I can cat /temp /meme bash. Oh, that's crashed in a way that it probably shouldn't have. Have I typed in my address wrong? Yes, I did. 736. Okay, fine. You get the point. It's always a bit fiddly. It never worked first time. Sorry. But you can see that you can overwrite it. And in fact, actually, to prove it's working, I'm not lying, if I look at the exploit.s string, you'll notice that this padding I had before, if I just copy and paste it, is exactly the same. I don't know if that lines up properly. Yeah, there you go. You'll notice these two values are exactly the same. This is actually how I wrote this exploit. I didn't do it with the source code, because the buffers are often sometimes it doesn't exactly align to the buffers it says it should. It's easier just to brute force the offset using the debrusion sequence. And then this address here was, as we showed, was the jump RSP, which does this. So, I mean, actually, nah. Let's see. Now, if you want to find somewhere to return to, you wonder, how did I work out this address, 41490C? Like, where did that number come from? Well, there's two ways you can do it. You can either look through with a cutter or some other disassembler and look for functions which do something you want. But if you look at the program exploit, if you look at the program repeat.c, there's not another function here. There's nothing good to jump to. So instead, we have to find the address of something we want to jump to. So there is a useful program called ropper, or you can use rop gadget. Those are the two things. So let's see, repeat. So that's just going to think for a bit. And you'll see it dumps out a whole bunch of really useful gadgets, bits of code followed by a return. So if we just have a look for some things which reference the stack pointer, that will take a long time to run too, but usually the useful stuff's near the top. I can get that. Well, I'll just clear it and restart. Let's go. So we want, that's it. So we could have something which was jumped to the stack pointer. Is that going to be in it? No. Well, the other way we could do it would be to push the stack pointer and then jump to it. Let's have a look for things that do that. Please work. Why are you not working? Every time. Don't see why this is not. Okay, fine. If we just grep the RSP, we can just manually search through some of the things until we see something we want. So I go to the top quickly. All this stuff is way too long. Here you have a pop RSP ret. That's useful, but it's got some other... Oh, where's it gone? It had some other stuff before it, so it's not desperately useful. Add RSP. And RSP and AL. Call REX. Call RSP. So that's another way we could do it, but that would push the call RSP would push the current return pointer. So I believe that actually just put the code into basically a permanent loop. Well, actually, I think that just does nothing, because you call RSP, it pushes the instruction of the next thing and then jumps to it, which should then jump to the instruction afterwards. That actually probably isn't no op. But you can use tools like this, and I can use rop gadget as well to find these useful instructions. So let's see. Take my word for it. There are programs to do it. I'm probably messed up the instructions. There's documentation for how to do this online. But anyway, let's go back to the instruction. So now we can do this. We can hack like any system in the world, right? Like we can take control of any program like a real hacker just by sending input. Well, not exactly. This is how it happened back in the 90s. People didn't have it in their head that this could actually happen, and they would read into buffers without checking the length of them, and they also set up executable stacks. To prevent, once the internet came along, it was no longer just a couple of people messing with your mainframe. People from across the world, even nation-state attackers, could just completely hijack your system with this. And so to address this, a bunch of security measures have been put in place. I'll go through those because they're really important to learn. Ah, dear. So, first one, address space layout randomization, or ASLR for short. This randomizes the address of data and code areas so that knowing where to transfer your execution to becomes really, really hard. This does make the code slightly slower, as it has to work off relative rather than absolute addresses, which involve an addition operation. But for the most cases, this is just completely unnoticeable performance-wise. This can also retroactively be applied to anything with this relative code, which covers pretty much any dynamic library, and covers anything which has had it manually set. This is, of course, also enabled by default at the OS level for pretty much all modern systems. In fact, that's why we had to use that gadget of pop. We had to use the pop RSP ret. It's like push RSP ret gadget, because otherwise there was no way I could work out where the stack was. It's randomly generated. Of course, this isn't always enabled. If you have static linking turned on, it will be disabled. If you can turn it off at the kernel level, if for some reason you have some old code that uses absolute addressing but pretends not to. But frankly, the only way of defeating this without an unreasonable time spent trying to brute force the randomness, which is done per process, is to somehow leak a known address from the area you wish to jump to, or try to partially overwrite an address by brute forcing a couple of bytes of the offset. Sorry, give me a sec. Luckily for an attacker, valid known addresses are at the end of every single stack frame as the return pointer and as the saved base pointer, allowing you to work out where the stack and the code segments are. But you need to still have some way of reading off the stack, which isn't necessarily guaranteed and usually doesn't exist in most programs. There are other ways of leaking pointers, but they're incredibly system specific, and I can't possibly go into them in a single talk. In many circumstances, of course, as I said, the static addresses mean that you don't have to do this because the static linking means you don't have to do this because the addresses are all fixed. Write XOR execute, otherwise known as data execution prevention, or DEP. This is the rule that you shouldn't have a page that is both writable and executable, meaning that pretty much every modern piece of software does not have an executable stack. In fact, I actually had to compile repeat with a special flag to disable this protection. If this protection was enabled, if I try to jump to the stack, we just crash, because it's not marked as executable. This can't be retroactively applied with complete reliability, as an executable stack is used in some cases. For instance, GCC, which is the most common Linux C compiler, uses an executable stack to implement nested functions, which silently disables this protection with no warning whatsoever. But that's quite rarely used, and is actually not part of the standard. So generally, this will be turned on. But instead of jumping to our own code, we can use something called return-oriented programming. The simplest thing would be to jump to another function that does what we want, so that we don't have to execute our own code, the attack I talked about at the beginning. Or we could just look around for a function or a piece of code that does a small bit of what we want, followed by a return, and chain the addresses of these things together to achieve a much more complex effect. The addresses of these code fragments and their associated effects and code are known as ROP gadgets, hence the tool Ropper and ROP gadget used to find them. I'll leave the specifics of ROP in a future talk because there are many online things for it, and this has already gone for like an hour, so whatever. However, if we can't find enough gadgets to achieve a desired effect or a function that does what we want, we're just stuck. We can't do anything but crash the program. And that's really powerful. That basically just blocks off this attack completely. It doesn't matter how long you brute force it, no matter what you do to the environment, you can't take control of the thing. But often with large programs, there will be enough gadgets and functions to achieve what you want, so it can't be relied upon, but it does make things much harder. You can't just jump to some shellcode. So let's have a look at stack canaries. These are probably the most scary protection for any person trying to exploit a system, because a secret value gets pushed onto the stack before the return pointer, so that overwriting it with a different value can be detected, and the program safely halted without transferring execution to an attacker-controlled address. To make this even worse, of course, the first byte is set to 0, known as ASCII armoring, which means that it can't be read by a function that is expecting a null terminated string, because it sees the null, goes, nope, this is the end of the string, and returns it, and doesn't go into the rest of the stack cookie, or stack canary, whatever you want to call it. That blocks most ways of leaking it, because most things that allow you to dispense random values from the stack are with string functions. Of course, trying to overwrite it with a string function hits exactly the same problem. You tell it to copy a string to something, it sees a null before your actual value of the stack cookie, and it can't write it. This 0 byte leaves another 56 bits lying around on a 64-bit machine, which in most cases basically is unbrute forceable. It would take you way too long to get into, and someone would notice. However, on 32-bit machines, this only leaves 24 bits, which is about 16 million, I believe, which is well within the realms of plausibility in many cases. Like, for instance, if you're on the same machine, it is quite possible to count up to 16 million by brute forcing it. But of course, if you're over a network, it takes a lot of effort to actually get to the place which has the bug. This might not be. So that's a more case-by-case thing. This, of course, does not affect overflows in areas other than the stack, so the heap or even global variables, or between variables within the same stack frame. So if I go back to this, I could overwrite the value here with 5 without having to go into the return pointer and mess with any stack cookies. This is really hard to bypass. You basically just, if you want to actually get round this, you have to put in a lot of work trying to find some way of reading a value off the stack, and generally that's just not even possible. But it does slow down your program a lot. Every time you return from a function, you have to check if the stack cookie is the same, which means reading a value from memory. Then you have to do a conditional jump, checking if it's the same. And if it's not the same, you have to then go into a exit routine that doesn't go through the rest of your program. And if you're doing a lot of tight function calls, so, an addition function that doesn't do much, having to, whilst, reading a value from memory doesn't sound like too long, compared to adding something to a register, that's a significant amount of time. You can actually have, for small functions, a huge slowdown with this. And so often these things won't necessarily be enabled for the whole program, which, of course, therefore loosens their ability to protect. But generally, you enable this, most vulnerabilities of this class, not necessarily all memory corruption vulnerabilities, like use after free we talked about before, you put one of these things on, there's basically no way around it. You basically just have to give up at that point. So, of course, there's one last thing, which is to actually do bounds checking. Make sure that you don't write past the end of a buffer. If you don't write past the end of a buffer, you can't be exploited by going past the end of a buffer. You should do this anyway, not even just for security reasons, because not going past the end of the buffer also causes many weird and wacky bugs that can turn up, minutes later in your program with no reference to where they came from, and change things in tiny little ways that disappear when you're trying to debug it. It's awful. It is technically a bit slower to do bounds checking, and doing too many checks when you've already checked something, checking it again, will cost an extra bit of time. But it is almost never that this is the thing that is slowing down your program the most. Don't bother spending time optimizing every single bounds check when there could be massive other bits of code you could be looking at first. Only do bounds checking optimization later on in your optimization process. And of course, bear in mind that other memory corruption vulnerabilities do exist. Again, I'll talk about that in a future talk, but they may not necessarily be prevented by bounds checking. For instance, use after free, as I keep talking about, isn't a bounds checking thing. It's a memory management thing, and it's completely separate. But doing bounds checking is pretty good as a preventative measure, and is very fast. So, there are a large number of tools and techniques that can be used to fix this problem. And developers who program in low-level languages are pretty much universally taught that at least something bad happens if they don't do bounds checking or put in these protections. So you could quite easily see that this isn't a problem anymore. It's all fixed. Not quite. The most common place for this sort of stuff is in JavaScript engines. They are a huge programming environment which allows very sophisticated attacks that could just not be replicated in pretty much any other environment. Things like cache timing and a whole bunch of other stuff that just can't be done remotely, or at least not sensibly remotely. And of course, browsers are massive code bases, often larger than operating systems or compilers, probably some of the biggest software out there, and so aren't very well audited for these bugs. And of course, JavaScript engines have to be very, very well optimized, and therefore they work very close to the metal, meaning that things like memory allocation start factoring into the code. And these bugs just keep turning up all the bloody time. You have, if you go and look at the CVE list for any browser of your choice, there will be about 14, 15 every year which is a memory corruption vulnerability that gets you code execution. This isn't like it occasionally happened in 2005. Last year, this year, you find these things all the time. So if you understand the vulnerability and you've got a lot of time to kill and you want to get some bug bounties, this is probably not a bad place to look. They also turn up in networking code. It's sort of the perfect target if you're a hacker, looking at the it receives remote input from completely unverified sources in a way that's often untraceable. It's exactly what you would want to go for. OpenSSL Heartbleed, you may have heard of, caused a massive panic through just a simple buffer overflow. TLS, which is the protocol used to secure most of the web, has a heartbeat command that acts very much like a ping. The server repeats a message you send back at you. OpenSSL, which is the most popular TLS library, forgot to check if your claimed message length was more than the actual amount of data it received. So you could just lie and say, I sent you 1,000,000 bytes when you only sent 5. Luckily, this check did not fail on the receive side, so it couldn't be used to modify memory contents of the server. Unluckily, however, it was on the send side, which meant that attackers could basically just read back past the end of the buffer arbitrary memory contents. These are your stack cookies, your return pointers, and anything else that they would keep in the same area. Actually, not stack cookies in this case, so this was on the heap. But it would still allow you to read random bits of memory contents. And for a server whose job it is to keep things secure, to store passwords, to store cryptographic keys, being able to read random bits of memory is really, really bad. And so, you probably all heard about the scare everyone going, oh no, the internet is ending. But we fixed that by releasing by just adding in a thing that checked if the length was correct. So, oh wait, no, I went too far. IPv6 code is famous for this sort of vulnerability. IPv6 is a lot more complex than IPv4, especially in regards to determining the length of a packet, and someone messed up. They messed up in OpenBSD, which is widely regarded as the most secure general purpose operating system on the planet. They've had like 2 or 3 bugs in their 20-30 year lifespan with which have been remote code execution on the default install. And this is one of them. It's very, very secure. It has some of the best people in the world looking at the code base. It's a very nicely built code base which is easy to audit. Yet this thing slipped through. And it was a memory write vulnerability, which could be used to have kernel level remote code execution. Whilst taking control of some random process inside the computer is quite bad, taking control of the kernel is way, way worse. The kernel has complete control over the entire computer, and it can read any file or any memory or interact with any physical device plugged into the computer that it wants. Story short, any security issue worse than kernel remote code execution usually involves someone being killed. It is awful. It is not what you want on your system. In fact, pretty much anything that takes user input can suffer. The strings program that I mentioned last time is beloved by hackers for its use in grabbing things that look like text from a program. It was vulnerable to this exploit. libxml2 is a commonly used library for parsing XML and HTML documents. It too was vulnerable. ext4 is the most common Linux file system, and its kernel driver was vulnerable. But I use Windows, and you haven't mentioned that yet. That's because I don't have enough time to give you the sense of scale of Windows buffer overflow RCE bugs. It's almost funny. SMB, used for Windows file share, was vulnerable to a buffer overflow exploit you may have heard of, known as Eternal Blue, which was used part of WannaCry, the thing that was used to take out the NHS a while ago. Not good. Windows Codex library, which handles video, was vulnerable to this. The bloody font library to the OS was vulnerable to an attack of this form. And this is just the OS. I haven't even started talking about the common apps on Windows with similar issues. This is the stuff which comes pre-installed on your computer. And I know there is someone out there saying, but I use a Mac, and they can't be hacked. No. Mac's Bluetooth system was vulnerable, which led to remote attacks that looked like something straight out of Hollywood. I would really recommend watching the video. It is so cool. Someone just taking over a computer just with a Bluetooth device. OS X NFS driver, a system used for accessing files over the internet, was vulnerable to a kernel-level exploit, which could be used by a process on the system to get kernel-level permissions, or if you try to connect to a remote server, would give that server complete control over your entire system. Not good. Mac's ICMP implementation, which is the protocol that controls pings, amongst other things, was vulnerable to this stuff. And there is much, much more across all platforms and systems. Anything you have heard of will have had something like this before. And it is still ongoing, and it is still a huge problem. But it is getting better. By being aware of the vulnerabilities and thinking like an attacker, you can prevent 99% of these. This is what I think we aim most for in CyberSoc, is the idea of when you're writing a program, step back and go, how could someone exploit this code? What could possibly go wrong? And writing your code to protect against it. And by using the protections I talked about earlier and proper bounds checking, you can almost eliminate the final 1%. There will still be a bit left over, you will still mess up somewhere, but you can minimize that risk. And of course, most people are using no, that's not the right word, high-level programming languages that don't give the programmer enough control to create these vulnerabilities. However, you have to be careful though, because if the lower level interpreter or compiler is written, which is written in a lower level language, it must be, if that is vulnerable to a buffer overflow exploit, or the libraries that you link into your Python or Java or what else is written is susceptible to some form of memory corruption vulnerability, then the whole thing is vulnerable as well, and in a way that is outside of your code and very difficult to find. And of course, people find novel ways to screw up in even the most safe of environments. I mean, PHP is the classic example of being a language with completely safe string manipulation, which basically eliminates this sort of bug altogether. But if you speak to any security person about PHP, they will give you a very angry look, because PHP has had a vast number of security vulnerabilities with people misusing functions, executing user input as if it was code, all that stuff. So just because you're using a high-level programming language does not mean you can't be hacked. Please don't take that away from this talk. Please just keep in mind that it reduces the chance of this vulnerability being your fault. It can be someone else's fault, but it's unlikely to be your fault for this specific class. And of course, red teaming and security audits are becoming a lot more commonplace, and it's even seeping into the public consciousness. I mean, 10 years ago, if you'd asked the Guild to allow someone to host a single talk on hacking, let alone run an entire society based around it, they would have laughed at you, whilst calling the police. Now they only laugh at us, and occasionally ask us on calls to check we're not breaking the law. But frankly, this is definitely an improving situation, but we need to keep aware of the sort of things that can go wrong, and we need to keep aware of the ways we can fix it. So, now you've had a chance to look at all this stuff, you can try it out. We've got a CTF with a bunch of challenges. The formatter one you probably won't be able to do with just the stuff in this talk. You'll need a bit more for that. But the other few in that section, in the Pwn section, should be pretty much open to you now. There's exploit exercises. It's a really good resource to practice some of this stuff on in a very well documented environment. Live Overflow is an amazing YouTube channel which taught me pretty much everything I know about binary exploitation. I'd really recommend checking him out if you want to have some extra, someone who actually knows what they're doing explaining this. And of course, you can chat to us on the Discord.